In the quiet of space, while humanity celebrated on Earth, a lone spacecraft was braving conditions no machine had ever endured. No bigger than a small car, yet traveling faster than any human creation in history. Nearly 430,000 miles per hour. It was on a mission to do the unthinkable: touch the sun. This was NASA's Parker Solar Probe, and it was not merely breaking speed records. It was plunging directly into the sun's outer atmosphere, the corona, a region so extreme that even light itself struggles to reveal its mysteries. For the first time in history, we were no longer just gazing at our star from a safe distance. We were inside its breath, surrounded by its blazing winds. What Parker captured there was not just breathtaking, it was alarming. With the help of artificial intelligence, scientists decoded the probe's most daring images, and what emerged challenged the very foundations of solar physics. Parker revealed colossal eruptions colliding like titans in space, spiraling magnetic structures twisting with impossible elegance, and violent switchback bursts cracking through the solar wind as though space itself was folding. These weren't just spectacular sights, they were signs that our understanding of the sun, and its power over Earth, might be dangerously incomplete. The December 2024 flyby marked a turning point. Parker had ventured closer than ever before, just 3.8 million miles from the sun's surface, and its wide-field imager, known as WISPR, recorded the solar wind at the moment of its birth. Each streak of light in its frames was a stream of plasma, particles accelerated to hundreds of miles per second, carrying magnetic energy that stretches across the entire solar system. And within this torrent, Parker caught something extraordinary. 3 coronal mass ejections, immense explosions of plasma and magnetic fields, erupted within hours of one another. Normally, we only detect these storms after they have already expanded far into space. But Parker watched them rise in real time. What the AI analysis revealed was even more startling. Instead of traveling separately, the CMEs collided, fused, and gave birth to what scientists call a cannibal CME. A single monstrous eruption, amplified by their union, surged outward with terrifying force. But the revelations didn't stop there. Alongside this eruption, the probe's instruments captured a glimpse of the heliospheric current sheet, the sun's vast, spiraling magnetic boundary. Imagine a ballerina's skirt twirling endlessly, stretched out over billions of miles. This invisible frontier shapes the way solar winds spread through the solar system, and when aligned with an eruption, it can act as a direct highway funneling solar energy straight to Earth. AI analysis of Parker's data revealed that this current sheet is far more chaotic at its origin than anyone had suspected, twisting, folding, and reshaping itself in response to deep magnetic surges within the sun. This turbulence could mean the difference between a harmless light show in our skies and a storm capable of crippling Earth's technology. Back in 2018, Parker had discovered strange zigzag reversals in the sun's magnetic field, known as switchbacks. At first, scientists thought these were random, chaotic turbulence. But during its latest approach, the AI uncovered repeating patterns, organized waves of switchbacks that aligned with the timing of CMEs. These were not random after all. They may be the missing link to one of solar physics' greatest puzzles: why the corona is hundreds of times hotter than the sun's visible surface. If switchbacks act as channels, they could be pumping vast amounts of energy into the corona. But there's a darker side: if they also amplify eruptions, they may play a hidden role in triggering some of history's most devastating solar storms. Reaching these discoveries required unimaginable engineering. Each of Parker's daring passes was made possible through gravity assists from Venus, slingshotting it closer to the sun and boosting its speed beyond any spacecraft before it. On this last pass, its carbon composite heat shield endured temperatures of 2,600 degrees Fahrenheit, 1,400 degrees Celsius, while radiation levels bathed its instruments with intensities lethal to normal satellites. Yet Parker survived, and with the aid of AI, it returned more data than human analysts could ever process on their own. And then came the anomaly. As the AI combed through the solar wind data, it uncovered something no scientist had ever seen before: a vast, elongated void, an immense corridor of near-total emptiness in the solar wind. A sharp boundary stretched for millions of miles where particle densities suddenly dropped close to zero. Even more unsettling, this cosmic vacuum appeared directly downstream from the cannibal CME. It was as if the eruption had swept the solar wind away, carving a tunnel of nothingness through space. If such a corridor were to connect with Earth's magnetic field, it could weaken our shield, leaving our planet exposed to cosmic radiation and solar energetic particles. Even fainter, buried in the data, were tiny oscillations in the Sun's magnetic field. Too subtle for human eyes, they had been dismissed for years as background noise. But AI revealed their rhythm, faint pulses repeating in ways that suggested deeper layers of solar activity rippling outward into space. Were these whispers from the Sun's hidden interior, or signs of a process we have yet to name? For now, the answers remain uncertain. But Parker's solar probe has shown us something undeniable. The Sun is far more dynamic, volatile, and unpredictable than we ever imagined. Each orbit brings us closer to truths that could reshape not only solar physics but the way we prepare for the storms that may one day decide Earth's fate. The world above us has always looked steady, eternal, and predictable. The Sun rises, the Sun sets, and its light has nurtured life for billions of years. But Parker's solar probe has shown us that behind that familiar glow lies a restless, volatile, and sometimes terrifying force. During its closest approaches, Parker's instruments, paired with artificial intelligence, revealed something remarkable hidden within the chaos. A repeating pulse, a kind of magnetic heartbeat. Every 142 minutes, the Sun seemed to send out a rhythm that echoed across multiple measurements. Magnetic field shifts, velocity changes in the solar wind, and even faint light fluctuations recorded in ultraviolet wavelengths, all of them pulsed in unison. This suggested that deep within the Sun, some coherent global process was breathing, modulating the outer layers like a hidden clockwork. Some scientists immediately linked this heartbeat to the long-observed solar cycles, the mysterious 11-year ebb and flow of sunspots, flares, and storms. If the connection is real, then this heartbeat might not just be a curiosity. It could serve as a predictive tool, an early warning system for the violent eruptions that sometimes lash out at Earth. But an unsettling question lingers. If the Sun has been pulsing all this time, why are we only hearing it now, so close to the fire? Among Parker's most dramatic images was a vision almost too vast to comprehend. A filament of plasma stretching nearly 2 million kilometers across the Sun's surface. Normally, such structures collapse back downward, unleashing modest eruptions. But AI-assisted analysis suggested this one was unstable, its magnetic roots weakening in a way never recorded before. If it broke free, it could hurl a coronal mass ejection far more powerful than anything Parker had previously seen. A storm on this scale, if aimed at Earth, could rival or surpass the legendary Carrington event of 1859, when telegraph wires sparked into flames and auroras blazed across the tropics. In today's fragile, interconnected world, such an outburst could disable satellites, cripple global communications, and plunge electrical grids into darkness for weeks. Yet the most puzzling discovery did not come from images at all, but from Parker's final radio transmissions. Hidden in the telemetry was a strange, narrowband signal, structured, repeating, and unlike anything associated with the spacecraft's instruments. Its origin appeared to be local, from the very space Parker was passing through. Some researchers cautiously suggested it was a natural resonance of plasma shaped by the Sun's magnetic fields. Others were less certain. The signal's timing, arriving exactly as Parker skimmed the most hostile region of the corona, hinted at processes we do not yet understand. And so the questions deepened. Was it a natural phenomenon amplified by magnetic forces? A resonance never before detected because no machine had dared venture so close? Or was it something stranger still, a phenomenon that defies the physics we currently know? For now, the signal remains an unresolved whisper, locked inside the final fragments of data Parker managed to send before its mission ended. The probe was never meant to return. It was a one-way dive into the most brutal environment any spacecraft had ever entered. Its task was simple in words, but monumental in practice. Find out where the solar wind begins, why the corona burns hotter than the Sun's surface, and what drives the colossal storms that sometimes batter our planet. It achieved that, and more. It revealed cannibal eruptions of plasma merging into storms of unimaginable scale. It uncovered the sun's hidden heartbeat. It watched a colossal filament prepare to break free. And it carried with it the riddle of an unexplained signal from the edge of hell. Parker's journey has ended, but its legacy has only just begun. The data it returned will take decades to unravel, reshaping what we know about our star and perhaps even how we prepare for the storms that could one day threaten our civilization. The sun, once thought to be steady and dependable, is in truth alive, restless, and sometimes dangerous. Our future may depend on how well we learn to listen to its pulse, and how